So in this talk, I will mainly focus on the recent innovations we have made, but in order to give you the context, I want to also run through what we have been doing and how really we get the ideas, the innovations based on characteristics modes analysis. So smartphones are everywhere, as we know very well. We use it for many nice applications. We use it to keep in touch with our families and so on and so forth. We complain about our kids spending too much time on smartphones. They obviously find that it is very useful, but then we set the examples of using the smartphones a lot ourselves, even during dinner tables. So smartphones is without any argument, something that we use very much in our lives. We have found it very, very useful. And it turns out that smartphones can perform all these functions very well because the data rates can be very high. And MIMO technology is the key to providing these high data rates. So MIMO is no stranger to many of you, but just to emphasize again that MIMO is very popular because it allows us to scale the data rates linearly with the number of antennas that we have. So some days ago, I decided to just write a few lines of MATLAB code to show this more explicitly. We have a channel which is quite ideal. When we talk about channel coefficients, they are uncorrelated complex Gaussian, then we are talking about rich scattering channel in general. Non-line of sight rich scattering channel. So this is basically what we can see in real life, not just a mathematical construct. And you can also assume, for example, there is no channel knowledge at the transmitter. And for fixed total transmit power. So under such conditions, we can run a simulations and see that indeed the data rates or ideal data rates and average over many realizations of the channel scale linearly with the number of antennas. And for M by M system, MIMO system, we can see that indeed the performance is quite fantastic. And this is the reason why MIMO system is so popular. But with regard to wireless communications and cellular communications, the price to pay not only is that we need to do some more processing of the signal, but a big price to pay is that you need to have multiple antennas at the smartphone at the same frequency. So previously you have multiband for example, to have coverage at the low band and high band and so on. But now you need to have multiple antennas at each band to realize MIMO system. So is it challenging to design a MIMO antennas for smartphones? There are many practical challenges with respect to antenna design here, because you need to, first of all, put in more antenna elements, or at least more ports. So this makes it difficult for one to design the antennas, because you need to have more antennas for the same real estate. You have the same chassis where you have to put in more antennas. Not only that, we know that for cellular applications, you need to have multi-band. And these bands are usually rather wide band by cellular standards. So we also need to make the smartphones slim, because that has been the trend. Of course, not too slim that it is not mechanically stable. We need large display, because that has also been a trend, that people want to see the display covering the entire front side. Metal bezel will also make it harder to design antennas, because now you put more metals in the places where you would otherwise have put antennas, and then you need to put in a lot of components, microphones, speakers, and so on, and a lot of cameras these days. So a lot of antennas is needed, and these antennas are not just narrowband, but you need also wideband, reasonably wideband antennas. And there's not much suitable space, so we need to have innovations in order to come out with good solutions. And this is just a picture I found from the internet of iPhone 11. And you can see here some places where they are putting the antennas. So it's really quite difficult to find space to put in the antennas. So if we look at how people have been designing terminal antennas, mostly, usually you start with some requirements. And for terminal antennas, you are mostly looking at omnidirectional because you don't want it to be sensitive to orientation of the user terminal. And of course, you want bandwidth to satisfy the multi-band requirements. You want then to design the antennas to be fitting into some given space. And of course, we then go on to put in some basic antenna types. Usually, it's kind of monopole, PFAR, some variants of these. Or you tried to use previous design to customize it by experience intuition. Then you put in the components and see what they do to your antennas, and you tune the antennas back to the required bands. You test the antennas to make sure that they radiate properly, they receive properly, and you check that they are safe with respect to SAR exposure. And in some places, you need to check the hearing aid compatibility as well. So you have a checklist here. And if everything goes well, fine. If not, then maybe you need to tweak the antenna. So what is the innovation here in this process? It is mainly in this step where you have some experience, intuition, and this is based on the fact that these antenna engineers have been doing this for years and years. So they gain this intuition into how maybe by cutting a slot here, doing a shot there, you can meet the performance requirements. And in fact, maybe just meet the performance requirements. If you ask them why exactly would this work, they may not be able to give you a very good answer. For me, who has no background experience in antenna design, this is like black magic. So how can we innovate if we do not have this kind of experience and intuition? And we had a chance to try to innovate with our intuition when we tried to build the first MIMO antennas for compact mobile phones, and which are also multi-band, the low and high band. So how we did that was by means of mix and match. So we could take different kinds of antennas, multi-band antennas which are working. Most of them are internal multi-band antennas, so they can fit into the casing of this antenna. Some of them, like this one, stop here, will require some bit of protrusion from the casing. And we try different antennas, and we try to understand how to get a good antenna performance from such different kinds of combinations. This was work done together with Sony back then. And one thing we learned from this study of trying to mix and match is that no matter what we do, for the low band at 850, we have always quite low isolation, right? No matter what type of antennas you use and so on. And this usually means you have quite high correlation. And with high correlation, you have not so good MIMO performance. Of course, isolation itself will penalize on your total efficiency as well. So it took us some time, I guess 2 years, to look around and try to find out what is the problem behind this. Now, the issue is that if you were to put two dipole antennas which are parallel across this terminal, you have still a spacing of about quarter of a wavelength. We won't expect such poor isolation performance even for dipole antennas which are placed parallel with this spacing. So what is really the problem here? So we figure out that theory of characteristics modes can give us the answer. So what is theory of characteristics modes? Well, it's a way for us to find the current modes of a conductor object. So in our case, it is a chassis, the metal chassis where we build our antennas from. And we find the current modes by solving a generalized eigenvalue problem. And that is based on the real and imaginary part of the impedance operator. So what is interesting about this eigenvalue problem is that if you choose to solve this problem, inherently these current modes will give you orthogonal far fields. So orthogonal far fields is very interesting because for MIMO, if you have orthogonal far fields and you have a rich scattering environment, that will give you low to zero correlation. So how do we find the how do we use these modes? Essentially, first we try to find these modes by solving for the eigenvalue problems. And it means that we are finding the resonance property of the conductor object. So if we have a dipole like this shape here, it's a strip we can see as a shorter dipole, then we can solve this problem at different frequencies. And if we confine the eigenvalues to plus minus 40, you can see that at this frequency, you only have one eigenvalue that is of this small value. And when this eigenvalue crosses zero, right? This is, we're solving this across frequencies. So if we trace how this eigenvalue is going, then when it's zero, that's where the resonance is. So if you look at the current distribution, if you look at this current here at resonance, for the first mode, we can see that it's effectively a half-wave dipole. And the far field pattern is a donut pattern. And if we look further, we can see that the second mode starts to be resonant at higher frequency, and it's a full wave dipole mode. And the current, as you can expect, is maximum at two locations that are off-centered. And similarly, if we go for the third mode, it's a 3/2 lambda dipole mode. And here we have 3 maximum for the currents. So this is, of course, an example where you don't need to use characteristics modes. You can figure out what the modes are. But it tells us that characteristics modes allowed us to really be able to find the resonance of an arbitrary shaped object. So it doesn't have to be a regular shaped object, which is why characteristics modes can be very interesting. So for example, if you have a flat plate here, it's like a flat dipole. So since you have more width of this dipole, you can have more modes coming in, including some kind of loop mode, which is this mode over here. But still, if we look at the 100 by 40 millimeter chassis, there is still only one resonant mode below 1 gigahertz, which is lambda 1 here. So in order to understand the isolation problem, let us look at the electric field 5 millimeter above the chassis. So if you look at the electric field, you can see here that the maximum of this field is at the short end of the top and the bottom of the chassis. So normally when we want to put two antennas, we try to put them maximum separation away from each other. So we put them in these two locations. But often what we do here, we put in antennas which will feed in an electric field sense. So what we do is we excite, by using this antenna, we excite the chassis with its fundamental mode. And we put a second antenna, and it's exciting the chassis for the same mode. So it will couple to each other like crazy because we are exciting effectively the same mode. The reason we do not couple completely, because often we do excite some other modes in some lesser extent. So the two exciters at shorter edges look more like this. So two dipoles, they are very close to each other, and they are not completely on top of each other because we still have some other modes we excite. It's definitely not this kind of configuration. So for us, this was a very nice insight. And how can we solve this problem then? Well, the solution is not so intuitive in a sense, because now we can move antenna 2 to the center of the chassis so that this antenna will no longer excite the same characteristics modes. It will just behave as a self-radiating element without relying on the chassis, which is why the isolation can increase, but because now if it has its own, uses its own size for radiation, it's very narrow band because it's just a smaller antenna. So you can see here that originally we have this curve for antenna 2, but very high isolation. If we move it to the center, we have isolation of 10 dB now, but the bandwidth is much smaller. So the price you pay is that you trade isolation with bandwidth. And there are some other ways to do this, to trade isolation with bandwidth, but we basically say that we are ready to sacrifice on bandwidth. Because so far I have shown you a 2-port antenna design. This port we can get very wideband based on that mode that we are using of the chassis. We can get isolation, but the bandwidth is not very good, and it is not useful for cellular applications. It's too narrow. So using characteristics mode, we find out that we can innovate. We can use the insight from characteristics modes to help us. And how do we do that? Now, TCM shows us opportunities for resonances that we know. So for the smooth mode, this is a dipole along the length of the chassis. And if we notice the region of interest, there is another mode which is nearby. It's a capacitive mode, which is a dipole along the width of the chassis. So the current is flowing along the width of the chassis, and the dipole is pattern is rotated because it's now 90 degrees rotated with respect to this one, right? With respect to the current direction. So in order to make this mode useful, we want to make it resonant. And by adding 2 strips along the sides, longer sides of the chassis, we managed to load this mode so that it is now resonant. So now we have a new mode which is under 1 gigahertz. And to throw into this mix, we actually get another mode as a bonus from the slot that is created by the strip. So now we have 2 new modes. So we have now enough modes, but how do we feed them? How do we excite them so we can have 2 antennas that are behaving well? So first of all, the fundamental mode, the dipole along the length, we can use a simple conventional radiator. And for port 2, we can excite the modes 2 and 3 because we notice that the electric field is high at this region. So we put a capacitive coupling element here. And therefore, we can get the wideband mode, as you can see here, but also this narrower band one, but a dual resonance mode, which has much better bandwidth than what we have seen before. From 2% bandwidth, we can get 9% for the second mode, and we have quite good correlation performance. We found that it is quite good when we evaluate the performance against some realistic practical conditions. We even managed to extend this idea to multi-band operations and so on. So now we have a 2-port MIMO antenna. The first port is wideband. The second port is improved to 9% bandwidth, but it is not quite enough because with the newer developments, LTE low band now requires up to 30% of bandwidth if you want to cover all the bandwidth, all the bands below 1 gigahertz. And also there has been more developments because from LTE advanced onwards, you need also as wideband for the uplink as for the downlink, right? So previously you only have MIMO for the downlink, but from release 10 onwards, you need also the same bandwidth for the uplink. So you need sort of the same bandwidth for both ports. You need to have low profile because since then, this height of the profile of the smartphone has become smaller. We have less antenna space because of the off-ground clearance. Because of the large display screen, we cannot extend the antenna beyond the edge of the chassis by as much. So how can we get help from TCM? Can we innovate more with the insights that we can get from TCM? Well, first of all, we want to reduce the profile, right? We can reduce that if we start with a strip-loaded chassis, which I did in the last design, and we reduce it from 8 mm to 4 mm by folding the strip. And of course, this means that we are constraining the freedom, making it a tougher problem by having the strip to be closer to the chassis. So we have a steeper behavior of the model curve. But it doesn't matter. We still can get quite good bandwidth out of this. And we want to design also a simple two-port feed. Previously, we used a conventional antenna for the mode 1, the wideband mode, and we use a capacitive coupling element for mode 2. But we want to make it even simpler so we do not rely on these extra elements. We want to incorporate it into the design. Can we do that? So we examined the electric field magnitude 2 mm above the chassis. And if we look at how the distribution of the magnetic field looks like for the Z direction, for modes 1, 2, and 3, we can see that the maximum, or we can have quite high electric field strength, which is away from the center of this strip, right? So in this region and in this region on both sides. So we can excite all 3 modes if we have a feed that is off-centered but along the strip. So we can excite these by using a prop feed. Now the other consideration is that we want to have 2 ports antenna, which means that these 2 ports should be orthogonal in terms of the radiation pattern they provide. Now in order to do that, we can put the prop feed on the opposite sides, where for mode 1, we excite them in phase, but for mode 2, these prop feeds are exciting them, the 2 locations with 90 degrees offset in the phase. So this allows us to have 2 ports which are exciting all modes at the same time, but between port 1 and 2, because of these performance here, we can get orthogonal ports. So, so far we have a simple prop feed, no added coupling element. We have same bandwidth for both ports, but the bandwidth is limited because the mode 2 has limited bandwidth. So what can we do? We notice that there is a new mode at the higher band edge, and we find this to be useful for our purpose. It has this pattern, bidirectional, and by noticing this current distributions, we can in fact tune this mode to our purpose by adding some slots. But before that, we also noticed that the prop feed we have chosen actually allows us to have 2 orthogonal ports, and it excites this 4th mode as well. So we can keep the prop feed, which at the higher frequency edge is still exciting the mode 1, and at the higher frequency edge is exciting mode 4 at opposite out of phase behavior. So now the design is such that we can have 1 port here and 1 port here, which is orthogonal, and we can, by adding the slots, tune this mode down to where we want it to be. So 2-port design with 25% bandwidth, low correlation, low profile, no separate exciter, no decoupling structure. So we are pretty happy with this performance here. But we need 30% if we want to fulfill all bands below 1 GHz. And if we look at the literature, what we have found is that our design is competitive to most of the design here, except for one, especially from the point of bandwidth and low correlation. So we then saw that, well, this other design is using a larger ground plane. So we tried a larger ground plane, and sure enough, we can get the same bandwidth. But then we have other benefits from the design that we have come up with. So we have now 25% bandwidth for the smaller chassis size, but we still have only 2 ports. We want to have more ports, and how do we do that? So we can, again, go back to characteristics mode analysis to look at what is contributed by the screen, which is traditionally seen as a problem. So if we take into account the screen, which really can be modeled by a metal plate, say it's a 2-plate thing with some shortings between the plates, and we find that we have 2 new modes that are created by this 2-plate structure with the added pins. And if you add the pins correctly, you can tune characteristics mode 3 so that it brings it closer to the other characteristics mode that is formed by the 2-plate structure. And now we can use a probe feed at this location to create dual resonance. So now we have a 3-port antenna. Port 2 is excited by a differential feed with the added strip, so we can add 2 feeds here for excite characteristics mode 2. The traditional mode is excited by a capacitive coupling element, and we add the matching network as can be seen here, and we get very nice isolation, at least 13 dB, quite good bandwidth over all ports, and efficiencies that are over 17% and correlation 0.16. So we have all this being obtained, and I think there are more to be done. In fact, we have more results that we hope to be able to present to you soon. So I just want to conclude by saying that smartphone antennas are very challenging to design, but we can go to characteristics modes, which can give us a lot of information. So even if you don't have all these years of experience, I think we can come up with a very nice design just because we make use of this information in the right way. So there are more opportunities for characteristics modes to come up with new innovations, not only in smartphones, but in other antenna design problems. And there are more theories that can be improved to deal with a larger set of problems. So I would really encourage you, for those who are interested, to consider extending the boundaries of characteristics modes research. Sorry for taking more time than expected. I will be very happy to answer any question.
Okay, thank you, Vince, for these very interesting presentations. Indeed, I can already see a few hands raised. Please go ahead, Ray.
So who has raised a hand?
I have a little hand, so you might see a little blue hand on the side. If you want to ask a question, please raise your hands. I saw a little blue hand with Ray written, but
I didn't see any hand. Not on my Zoom screen.
no, I think he lowered the hand afterwards.
Okay.
Are there any other questions?
Simone.
Yes, sure, Kapil. Please go ahead. There is Simone as well.
Hi, thank you for very insightful talk. I have a very a question that is related to, can we exploit the wideband antenna behavior with the help of TCM when like multiple modes are merged together for the wideband response?
Yes, and that is what I did with one of my earlier design with the strip. So what we did was that by adding the strip, we found out that we can, let me go back to it. So you can see here that this is a dual resonance, right, for the port 2. And
yes,
this is because we managed to find not just one, but 2 new modes by adding the 2 strips. So because these 2 new modes have high electric fields in this region, by having a CCE here, capacitive coupling element here, we can excite both modes. And since they are slightly offset in frequency, we can use them as a dual resonance to have a wider band port through. So yes, you can do that.
What if the bandwidth is more than 50%? Because like for 30%, we can like give some insight. But what if the antenna bandwidth is around 70% or 80%? I'm talking about impedance bandwidth, by the way.
Yeah, well, then you are talking about ultra wideband antennas. I think below 1 gigahertz. I mean, what we can do with characteristics modes is we can understand that there are not so many modes to begin with, right? So we can do our best to make use of the available modes. So I think it's not so realistic to go much beyond. Of course, as I show you, I mean, if you consider a larger ground plane and all that, it can make the design problem easier. But we should be aware that there are limitations. That's just physics, right? You cannot go beyond some fundamental limitations.
Okay, I have one more question. Like we have a rectangular PEC plate, and we are like looking at 10 different modes. If we introduce a defect on the plate, can we like get rid of some of the unwanted modes? Is this a proper way, or there are some other way to like get rid of unwanted modes in the?
Oh yeah. You can get rid of unwanted modes, and this is like the work that, for example, is done by Lin Fenghang and so on, where the unwanted modes may cause distortion in the kind of patterns you want. So yes, of course, it gives you information to do that, right? Because you can, for example, try to stop the flow of currents for some modes, and you can sort of remove them. But of course, you have to be careful about what you're doing, and you can check it afterwards what happens when you do something.
Thank you.
Thank you. Simone.
Hello, hi Vincent. Thank you for
Simone.
the nice presentation, and it is really very interesting the effort you are doing, try to apply characteristics mode to more realistic platform as a smartphone. I was just wondering if you can comment. So I've seen that, for example, very small clearance is a big problem, and when you try to design antennas on smartphone, but also the presence of plastic and generally the presence of losses. Mm-hmm. We know it's a very hard task to face. I mean, strictly speaking, characteristics mode, I mean, so far in the commercial code can only analyze perfect electric conductors. But since I was start also to be interested in use characteristics mode also to provide some, let's say, innovation or hint when the antenna is close to like the head, for example. So to try to see new designs when the antenna is, I mean, in operative scenarios. I don't know if you have any thought or any remark about how we could exploit the characteristics mode or try to have, again, some physical insight when we place in a more complex environment than free space?
That is a very interesting question. Well, at least I'm very interested in that question myself. My former student, Zach, was putting quite a bit of effort in that field to try to find a suitable formulations to solve for the modes with mixed materials. We were successful to some extent, but I think what could be quite promising is the recent work done by Parsi from Aalto University. So if you will look at some of his recent work, he claims that he has been able to come up with a suitable formulation for mixed material, including the effect of losses. And it seems to be working. We haven't had the chance to try out design with his approach. But I would say that that could be a very interesting approach. There have been others, Yikai and others, and his collaborator in NUS as well. And some other people have also been looking at this. So maybe there have been some more recent work from these other groups as well. But with respect to if it's dielectric material on the smartphone itself, because the amount of material is not so much. I think it's generally okay to just consider the loading effects. So they will likely slightly detune your antenna to a lower frequency. It's just a loading effect. And they do not by themselves effectively form new modes that you could use. I don't think so. Yes.
Thank you.
Good morning, good evening, and good afternoon to everyone. First, I want to thank you, Marta, Divitha, and Vincent for organizing this event. It's a real pleasure to share some of my work on characteristic modes and MIMO antennas. So my name is Binbin Yang. I'm a new faculty at the Department of Electrical and Computer Engineering at North Carolina A&T State University. My talk today will be about application of characteristic mode theory to MIMO antennas. So first, I would like to briefly review characteristic mode theory. I believe Vincent has done a pretty good job reviewing this. So as you all are familiar with Harrington's work, basically he reformulated the characteristic mode theory using method moments, and based on that, for an arbitrary antenna or a scatterer, you can use method to formulate its EM response into a matrix equation that's shown on the top right. Typically, most of the problem we are solving, either antennas or scatterers, we would give an excitation, which is the vector on the right. And by solving this matrix equation, you can obtain the current distribution on the antenna or the scatterer. And that's a typical way forward problem. But Harrington reformulated an eigenvalue equation based on the method moment. Essentially, it solves a generalized eigenvalue equation as shown here. By solving this generalized eigenvalue equation, we arrived at a set of modes, what we now call characteristic modes, and they have the property of having currents orthogonal on the structure and the far-field patterns orthogonal, being orthogonal as well. And the neat thing about characteristic modes is once you solve the structure and obtain the model responses, you can pretty much expand the response for any arbitrary excitation. So it saves you a lot of efforts. Instead of repeating your simulation for different excitation, you can now reconstruct the response for arbitrary excitations based on the model basis. So to illustrate the idea of the model expansion, here, this is one example, perfect example, shows you how you can expand your model admittance, like your input admittance in terms of model responses. For example, in this case, in the figure shown on the right, I plotted the admittance for a dipole antenna, and the black dashed lines are the response at the driven port, and the red lines and the green lines are essentially some of the fundamental modes on this dipole antenna. And you can clearly see that how the total response is essentially following the model responses based on their contribution. And because of this model expansion, it naturally arrives at a circuit model that's shown on the bottom left, where your antenna admittance is now essentially a parallel connection of each individual model admittance. Another example of model expansion here is Q factors. Of course, when the total Q won't be a weighted sum of the model Q factors, but the stored energies and the radiated powers can be expanded based on the stored energy in each mode and the radiated powers in each mode. And for example, on the figure shown on the right, I still use the dipole antenna as an example. And each solid curve shown here are the Q factors of each individual mode on this dipole antenna. And the dashed black curves are the total Q factor, like I calculate based on the expansion of the model parameters, like the stored energy and the radiated power from each individual mode. And a third example here in terms of model expansion is on efficiency. Again, the same dipole antenna. The solid line shows you the efficiency for each individual mode on this dipole antenna. And with some approximation, we calculate the total efficiency, which is actually the inverse of the total efficiency is a weighted sum of the inverse of each individual model efficiency. And so the total efficiency we calculate is the red dotted lines, and the markers actually shows you the total efficiency if you calculate directly from a driven port on FECO, and they have pretty good agreement. So, all these examples essentially demonstrate that, with characteristic modes, you can pretty much access any parameters for an antenna. Of course, here I didn't show the radiation pattern. You can do the same for radiation pattern as well. So all the input parameters, secondary parameter like Q factor and efficiency and far field patterns, you can expand them once you know the model response. So before talking about my work, I want to briefly mention what MIMO antennas are and some of the design challenges there. So when people talk about MIMO antennas, typically there are two types. The first one is what we call multi-element antennas, where you have multiple radiating elements with each element having its own driving port. And the second category is what we call multi-mode antenna, where most likely all the ports share the same antenna aperture, and you're just playing with the feed locations to excite different modes on the antenna, essentially. And in today's talk, when I refer to MIMO antenna, most of the time I'm referring to the multi-mode antenna. And in terms of design challenge, it turns out you have a very limited number of broadband modes. For example, if you look at the Q factor plot, each frequency, for example, if you pick a frequency, you can see that you have a limited number of modes that has a reasonable Q factor. As you look at higher order modes, the Q factor increases dramatically. And another thing is, if you go to electrically small, the frequency is lower, your Q factor increases dramatically as well. And another challenge, of course, is also on the efficiency side. You have a limited number of modes that are efficient in terms of radiation. For example, if you pick a frequency, you can see that only a limited number of modes have a reasonable radiation efficiency, whereas for high order modes, the efficiency tends to degrade. And also, of course, if your antenna frequency, like the operating frequency, reduces your efficiency, all of the efficiency drops as well. So literally, you have very limited number of broadband modes and efficient modes on a given structure, especially when it's electrically small. And another big problem for MIMO antenna is mutual coupling. And basically, because all the ports, are essentially operating at the same frequency, it's almost impossible to achieve ideal isolation between them. And any coupling would mean that some of the energy that you send into one port will be coupled to nearby ports and dissipated there. So therefore, your system efficiency is going to be reduced. And there are other problems like impedance matching and caused by the impedance mismatch caused by mutual coupling as well. But those are the design challenges. And before talking about our approach on MIMO antenna design, I want first briefly talk about how we apply characteristic modes theory to MIMO antenna modeling. So in terms of antenna modeling, for single port antennas, I think it's well established, right? You can model for a single port antenna, you can model its response as a parallel series resonance in parallel or parallel resonance in series. And with circuit models, we get the benefits of gaining insights on the antenna operation, and sometimes a circuit model can facilitate broadband matching circuit design as well. And in this case, we're looking at circuit modeling, specifically using characteristic modes because it gives us a pretty big advantage, because with a characteristic mode analysis, right? As I mentioned earlier, you can always reconstruct the antenna response with just one characteristic mode calculus. So for circuit modeling here, if you develop a circuit model for an antenna, and it essentially facilitates the calculating of the input parameters on the antenna aperture for any feed locations, any excitation combinations. So I think that saves a lot of efforts in terms of simulation for different feeding schemes on the antenna, for example. But like I said, antenna modeling for single port antennas are kind of straightforward, but it's not so straightforward for multi-port antennas. If you think about a multi-port antenna, for example, a 2x2 antenna, you don't have just one function as one parameter as a function of frequency. You have actually 2 or 3. For example, it's consider the reciprocity should be 3. So basically, you have an entry of a matrix. You have a matrix with each entry is a function of frequency. So it's if you think of just a random optimization in ADS or something, it's pretty difficult. But with characteristic mode theory, it turns out the physical insight helps a lot in this case. On the left, I assume everyone here are familiar with the formulation in characteristic modes. So on the left, what I showed is the self and the mutual admittance that are represented using the eigencurrents and the eigenvalues for an antenna aperture. And if you pick one node on the antenna and use that as your reference node, you can define the admittance for each individual mode, right? And you can also normalize your currents at other nodes with respect to this reference node. And if you do that, you can essentially simplify the expression on the left into the expression shown on the right. It's much cleaner now, simpler. And in fact, if you examine the expression, you can even write it in a more compact form shown as the way shown down here, where the YM is essentially a diagonal matrix where Y1, Y2, all the way to YM represents the admittance of each individual mode. And the A matrix is essentially the normalization matrix here, we mentioned here, between each port and the corresponding mode. So that's a pretty neat expression. That essentially says, your antenna port response anywhere on the antenna aperture that you observe is essentially a transformation of the model response, which is the diagonal matrix here. And it turns out the transformation relation we arrived at here can be represented using a transformer bank. On the one end of the transformer bank, of course, are the individual model admittance. On the other end of the transformer bank are the physical ports you are observing on the multi-port antenna. If you look at this circuit model, it essentially says that any input response you observe on the antenna will be a transformation of your model responses, nothing else. So, and that's a pretty, I think that's a pretty good and a beautiful observation here. As an example here, we looked at a 2-port wire antenna. One port is in the center, one port is offset a little bit. And we used the circuit model here, and we were able to pretty accurately model the S parameters of the antenna, and even the secondary parameter like Q factor. We achieved a pretty good broadband modeling as well. And then, we looked at so the antennas we looked at here is the the current distributions, and technically it can be applied to patch antennas as well. If you feed a patch antenna with multiple probes, you can you know, use the current distribution on the probes and the formulation mentioned here to model the patch antenna response as well. But one thing we realized is with the patch antenna is the eigenvalue spectrum actually changes slightly when you move your feed position. For example, if you look at the figure shown on the right, what I showed is the model significance. It's essentially another way of showing the eigenvalue spectrum, right? And so the solid lines you see here are the eigenvalue spectrum when I feed a patch antenna at one of the location R1 here. And when I move my feed location from R1 to R2, we actually noticed that the eigenvalue spectrum changed into the dashed lines. So what that means is, for patch antennas, if you want to examine your input parameter response at a different feed position, you cannot use the characteristic analysis you use for a different. For example, if you let's say you specify two ports on the patch antenna, you calculate the characteristic modes, you develop the circuit model, and now you say, I want to know what is the response at a different set of feed location. Well, unfortunately, the model spectrum is different, so you have to rerun the characteristic modes to find out what is the model like the expansion or model basis for that case. That makes this characteristic mode model expansion pretty much of no use now, because you have to rerun the full wave simulation for different feed locations. And we are thinking about this and wonder whether there's a more efficient way of modeling patch antennas. And we looked at the cavity models for canonical patch antennas, and we get inspired there. Instead of modeling antenna with physical probes, why don't we model the antenna without probes, and later on compensate some of the effects by the physical probe? So we actually reformulated the input parameters for a patch antenna using the characteristic mode analysis of a patch without any feed. And in the formulation, what we did is we basically use a current filament to model each individual probe. And I simplified a lot of the math here. If you're interested, you can go to the paper we published earlier and find out the details. But basically, it turns out you can expand your impedance in this form that is pretty much similar to the admittance, right? The only difference being that instead of using currents, now you're using the fuse under the patch. And one way of thinking E times the H is the height of the patch antenna here. So one way of thinking E times H is potentially the voltage between the patch at that point and the ground plane. Similarly, here you can specify a reference point. And once you specify, say, there's a reference point, you can define your model impedance for each individual mode. And you can normalize your field at any arbitrary position under the patch with respect to the reference point as well. And that's the coefficient gamma here. If you define those parameters, it turns out you can simplify the expression for impedance in the form that's shown on the right. And the first one is, again, the self term, and the second one is a mutual term. And this expression essentially boils down to the mathematical expression shown down here, where ZM is again a diagonal matrix with each diagonal entry showing the impedance of each individual mode, and gamma is a matrix defined based on the the normalization of the field. And again, so again, definitely you can cast this transformation relation into a transformer bank network, which is essentially what is shown in the dashed box here. So the Z1, Z2, all the way to ZM are the model impedance for each individual characteristic mode. And all those transformers and the transformation ratio for the transformer is essentially the coefficient or the entry of this gamma matrix here. And the only thing extra stuff that's shown down here are the, and here as well, are the DC capacitance and the probe inductance. Remember, we modeled the patch antenna without including physical probes. So when you actually try to, when you actually run the simulation in Fecal or any software, you have to include physical probes. Once you include the physical probes, you will introduce probe inductance, and you also introduce DC capacitance. That's why those extra items has to be added to the circuit model. But I want to claim that all those inductances and DC capacitances are pretty straightforward to calculate. There's no tuning you need to do. So, for example, the self and the mutual inductance expression is shown down here, and the DC capacitance you can pretty much calculate using a very simple static method moment code. So, considering those extra, the compensation for the physical feed, we arrived at these two expressions shown here. The first one is the self term, and the second one is the mutual term for the impedance of the patch antenna. And keep in mind here that the circuit model works for arbitrary locations. So once you calculate the characteristic modes for a given patch antenna, you can pretty much access its input parameters anywhere by to recreate the response there. You don't need to rerun any simulation. So as a verification of the model here, on the left, I showed you a pretty random patch antenna and arbitrary 2 ports. And using the circuit model, I modeled the 2-port S parameters and compare with the simulation, which are the marked lines. And we see pretty good agreement over a very wide bandwidth. And on the right, it's the same patch antenna. What I did here is, I first modeled 2 ports, and now I know, I calculated the 2-port S parameters. And then what I did is, I shorted one of the ports. You can consider that as a loading, essentially. And it turns out the response is pretty close. By loading the other end, now you just have a single port. But the response is pretty close to the simulation result, full wave simulation as well. So that essentially means that with the circuit model, we get a pretty accurate, highly efficient model for the entire patch antenna, and you can essentially play with whatever tricks you want. For example, if you want to design reconfigurable antennas, you can consider loading at any arbitrary locations. If you're considering designing multi-port antennas, you can test out different feed combinations. So the next thing I want to talk about is MIMO antenna synthesis, how characteristic mode theory can be used for antenna synthesis. If you look back at the circuit models we talked about, each one of the circuit model essentially indicates that the port response you obtain on a given aperture is essentially a transformation of those model responses. There's nothing more to that. So from that observation, we realized that instead of trying to optimize each individual ports, why don't we just try to engineer each individual mode? If you have the modes optimized, you can definitely get the best performance from the antenna aperture. So that's the philosophy behind the multimode antenna synthesis here. In this case, we took a electrically small rectangular patch as our example. So we pick a rectangular patch because we purposely we try to introduce some arbitrariness to this synthesis. You could have picked a square patch to make your life easier, but in this case, I picked a rectangular patch. And the design goal is to have 2 ports operating at a 2.4 gigahertz, and it's over a microstrip substrate. And of course, electrical size is less than half wavelengths by half wavelengths. So we did the synthesis, shape synthesis, without any feeds, just purely based on characteristic model responses. For example, if you look at the cost function, this is a cost function for each individual mode. All the terms we added are just model significance, which is something you can directly calculate from eigenvalues, and the Q factors, which is something you can directly calculate from the current distribution. And in this, the total cost is essentially, in this case, I consider 2 modes, so added 2 modes in the cost, and I added area here because I want to minimize the area occupied as well. And on the figure shown on the right, it illustrates how the optimization evolves as the optimization progresses. So we started with a coarse mesh and arrived at a pretty optimal geometry, and then in the secondary iteration, we refined the mesh and run an optimization with this new mesh. And then once you get a pretty good performance, we refine the mesh again and run the last iteration of optimization. The reason we did this is because with a coarse mesh, you can obtain a pretty close to optimal design much quicker compared to using a very dense mesh in the very beginning. And on the figure shown on the bottom left, I showed the model significance of the 2 modes. You can clearly see that 2 modes are resonant at the design frequency. So now you have found the optimal antenna shape. So of course, to design the 2-port antenna, you have to specify the feed locations. Luckily, we have developed the circuit models based on the discussion here, right? So you can pretty much run the characteristic mode analysis for this geometry, and then you can use the circuit model we developed there to quickly reconstruct the input parameters at any location under the patch antenna. So with the help of those efficient circuit model, I can now recreate what we call the S11 heat map. And on the heat map, you can clearly see where where is the location that will give you a good return loss. And here I picked one of the position as my port 1. And once you picked your port 1, you can move your second port around under the patch antenna and try to calculate how much mutual coupling is there between the 2 ports. And then based on that, I created a S21 heat map. You can call it a coupling heat map, something like that. And based on that, it indicates that if you feed your second port along the vertical line, you will have pretty good isolation between the 2 ports. So I picked my port 2 somewhere here, not only because it achieves a pretty good isolation, but also because it's in the region where you have a decent return loss. Keep in mind here, though, you can, we have some data that shows you can pick any other feed locations as well, not necessarily the symmetric case. But I picked the symmetric case just because it's pretty intuitively simple. And on the right, the figure compares the S parameter that was estimated by our circuit model and the S parameter that was calculated with physical feeds using FICO, and we see pretty good agreement between them. And this is the fabricated prototype, and we simulated HFS with actual physical connectors as a feed, and the measured data, which is the solid lines, actually agrees very close to the simulation results. And this is some of the far-field performance. Again, comparison between the measurement and simulation. So measurement are the solid lines, and the simulation data are the dashed lines. We see pretty good agreement between them as well. So lastly, I want to talk briefly about decoupling networks that was inspired by characteristic modes as well. If you remember, earlier in the talk, we mentioned that for a multi-port antenna, its admittance is essentially a transformation of the model admittance. And if you invert this, essentially you arrive at, you can say it's the same thing. Essentially, you can say, your impedance is a transformation of the model impedance as well. But anyway, given those transformation relation, it appears to us that, if you can design another network that inverse the transformation relation here, you can access each individual mode. For example, let's say this is the port impedance for a multi-port antenna. If you design another transformer network or transformation network that achieves this transformation relation, if you expand it, the input impedance is essentially the impedance of each individual mode. And here's another illustration for a two-port antenna. For example, for a two-port antenna based on the circuit model, you can expand it. You can represent it as a 2x2 transformer network with two characteristic port modes. It turns out if you include another network that inverses whatever transformation here inside the antenna, you can achieve the decoupling. So basically, in this case, the decoupling network is just a mirror of this equivalent circuit model. And if you look into port 1, you will see the image here, which is your first port mode. And if you look at your port 2, you will see the image here, which is your second mode model admittance. So essentially, our decoupling network is just a n-by-n transformer network, transformer bank. And of course, it just achieves the decoupling. It does not achieve the matching. So you have to add single port matching networks after the decoupling network. But this decoupling network combined with the matching network has the lowest degree of freedom for decoupling network of a n-port system. And this is an example, a numerical example for a patch antenna here. In this case, I introduced the coupling between the two ports on purpose, and you can see here is the mutual coupling between them. Before the, this is, the dashed lines are the performance without any external networks. So you can see that, the two-port antennas has pretty strong coupling between them. But by designing a 2x2 transformer network, that we can achieve the decoupling. And of course, you need to add single port matching. And that did a pretty good job in terms of decoupling and matching for this highly coupled system. And the figure shown here shows the first one shows the total reflection coefficient that is defined based on the Frobenius norm of the a two-port S parameter. And you can see that you have a pretty low total reflection at a design frequency when you include a decoupling network. The dashed line is the case when you don't have a decoupling network. And on the right shows the envelope correlation coefficient. Again, with decoupling network, we lowered the envelope correlation coefficient between the two-port antenna here across a pretty wide frequency range. So as a summary, here we demonstrate that you can apply characteristic mode theory to the modeling of MIMO antennas over a pretty broad frequency range, and you can also apply characteristic mode theory to multimode antenna shape synthesis. And lastly, we also talked about how you can design decoupling networks using characteristic modes as well. And in terms of future avenues for antenna design using characteristic modes, some of the things I can think of is potentially like dielectric antennas, periodic structure like the work that has done by Fenghan, and pattern synthesis. I see some researchers working on that. Dr. Yi Kai-jin and Dr. Hui Li, their groups have some work on that. And of course, substructural modes. Eventually, if you want to apply characteristic modes for some engineering designs, there probably are some structures where you don't want to touch. So that's where substructure modes can be helpful. Thank you, everyone. That's all I have. I'm ready to take any questions you have.
Thank you, Binbin. Thank you for this brilliant presentation. I think you have done a perfect combination of characteristic modes with circuit theory and combined also with matrix transformation with algebra. So I think it's very, very good work. Okay, so we are out of time, but anyway, I think it is worth using some minutes for questions. Is there any question? Any hand up? Yes, Amer, you can go.
Can you hear me?
Yeah.
Yeah.
Yes. Thank you very much for the presentation. It's impressive. And I have questions, maybe basic questions for you. So at a slide, I didn't know the slide, but it's below, before the slide number 10. You had a curve where you had the few modes and the efficiency. And what we see is that the efficiency is decreasing for all modes as the frequency increase, right? Is that this one? I thought the efficiency was decreasing. Maybe
yeah, the frequency was decreasing. If you go to electrically small, lower the frequency.
Okay. And so the higher the frequency, the better the efficiency, right? Not always. Okay. No, I was trying to see some physical insight, like what would be the reason why for all modes, when you get higher frequency, you get better efficiency in this case. But I see that for some modes, the efficiency is decreasing after that. The curve red and black is then decreasing after 600 megahertz.
Oh,
so
the red,
I thought, yeah.
I see. Yeah.
I'm trying to see some physical experience, like intuitive. You know what I mean?
Yeah,
like,
I see it. Yeah, very good question. So so first, the red and the black lines you mentioned here are actually the total efficiency. These are not model efficiencies.
Okay.
So as we mentioned, as you can see from the results we demonstrated here, your total efficiency will always be smaller than the largest model efficiency. So that makes sense. Like
so we can say that, yeah, we can say that for all modes, the higher the frequency, the better the efficiency, right? In this
that
case,
is what we observed here. I think it makes sense as well. As you go higher, your antenna is more electrically larger, and it's more inclined to be able to radiate efficiently, right?
What I thought is that each mode has its own frequency excitation. If I want to excite a mode, I have to choose a proper excitation method, feeding, and I have to choose the proper frequency. If I want to excite a specific mode, I have a frequency for this mode. So what I thought before, maybe I'm wrong, is that the efficiency should be the best at the excitation frequency of this mode. So when I saw this curve with different modes, different frequency, I was expecting to see like the best efficiency for each mode at its own frequency of excitation. If you know what I mean.
I see your point.
You know?
I see your point. So in the physical world, when you excite an antenna, you know, the efficiency you see will be a combination of different modes, and so I think in that case, your best efficiency is definitely around the location where your mode is resonant. In the model efficiency I plotted here, we are actually, you know, didn't consider any physical excitation. So we are assuming, you know, each mode is perfectly excited. So that's why you see a pretty high efficiency as the frequency increases.
But shouldn't we have? Okay, I understand that we don't have a specific excitation method, but shouldn't we have a maximum of efficiency at the specific frequency of the mode. Suppose I want to excite a mode which I have to choose this kind of frequency to excite it. Maybe I should expect the best efficiency at this frequency, you know?
I see your point. At least from the plot shown here, your efficiency seems to increase as the frequency increases. But you know, one thing I want to comment is not just the efficiency that matters, your impedance also matters, right? As you go, if the mode is resonant, for example, at 300 megahertz, if you try to achieve higher efficiency and excite a much higher frequency for that mode, you know, your matching may not be good, and also you may excite higher order modes.
Okay. May I ask another question if you don't mind?
Yeah, sure.
Slide 10 and 14, but we can start with 10. It is the same question, basically. Slide 10.
10?
Yeah, 10.
Here?
Yeah, this one. I'm like you have the admittance or like the left formula, top left. You have the admittance, and then you have the mod G, M, and GM. So you have two mods here, right? I'm just trying to see the homogeneity of, like, we have like admittance on the left side of the equation. So on the right side of the equation, how is it going, like, for the homogeneity? I'm trying to understand it intuitively.
Your question is asking how we move from the left expression to the right expression? Is that
no, right? my question is that for the left expression, only the left one, you have two sides of the equation. So the left side is admittance, right? YE, and the right side, I expect to have some maybe electric field, and then maybe something that makes sense in terms of dimension. And same thing for this equation as well, where you had your red, like on the top of your pen go up a little bit. Your pen go up.
Yeah.
Here you see this equation. This one YM equals this one. You have admittance on the left, and then on the right, I try to see how it can be admittance. You know what I mean?
So I see your point. So this is, I think, on the left is the typical way you would expand the model admittance using eigencurrents and eigenvalues, right? What I did here is essentially I picked one node, for example, node number P as my reference node, and I define all my model admittance with respect to that reference node. And then I normalize my current at all the other nodes with respect to this reference node. Because I already defined the model admittance here, I can essentially write it, simplify this expression, just write down my model admittance.
Okay, I understand totally that alpha has no dimension. Because alpha is GM divided, it has no unit, no dimension. GM divided by GM.
Just, no dimension.
So G is current, right? Is it current? G?
Which one?
G is current.
G?
G ou G?
J.
J, sorry, my accent is like...
Yeah, J is the current, yes.
Okay, so G square divided by 1 plus J lambda M, that is supposed to be admittance.
These equations are pretty much, I mean, people working on characteristic mode theory, they are pretty much used to those equations. So maybe because you're not so used to characteristic modes, it's it's typical of the characteristic, the impedance. I mean,
yes, voltage is 1 volt. If you use a unit voltage for the source, the admittance is equal to the current. Exactly. Not in units, but in magnitude.
Oh, okay, I should see it in magnitude.
It's the product between the current and the voltage, but the voltage is 1, I mean, so it's equal. You have the current.
I see what you mean. It's you have something, but it's equal to 1. That's why I don't see it here.
Yes, that's right.
Okay.
That's the dimension. Okay. That's why.
Okay, sorry. I'm not familiar. That's why. Yeah.
No. Thank you for the question.
Yeah.
Do we have other questions from the floor? From the audience?
Well, I don't know how to raise hand because I'm a co-host. Well, maybe that's why Vincent here. So I have a question. Actually, with respect to the decoupling network, you have this transformer network. How do you realize that in practice?
Yeah, that's a
page 25, yes, later.
Yeah.
Yeah. How do you realize that in practice, or you just kind of just do it in math, or did you realize that?
So so far it's just purely math. I haven't done any experimental verification yet, but there has been some radio frequency transformers available in the market.
Okay.
So there's something that's definitely you can verify experimentally. There might be some parasitics involved if you go to high frequency with a transformer, but theoretically, I think it's still something you can verify experimentally.
Okay. Yeah, I'm just curious if you have some kind of circuit equivalent implementation.
That's something, yeah, worth working on. Thank you.
Okay, thank you.
Yes, I have a question. Like when we are considering the transfer function of any network in the circuit theory, it can be represented by many forms. Like you can represent in the form of transformer. You can also represent it in the form of LC network or RLC network. So is it the only solution, or there are some other solutions which can get rid of the transformer and we can use a more simplified network which can be implemented in a planar network as well? Like, do you have any suggestion on?
I see your point. That's a very good question. So basically, your question is essentially kind of is equivalent to saying, can we realize those, for example, this transformation network, instead of using transformers, can we realize using some other LC networks?
Yes, it depends on which functions you are using. Like if you are using a Foster form or Kaur form, both can be solved with the help of any transfer function, but the resultant network is little bit different than what we are implementing.
I see. So based on the formulation we have here, I think the natural way is using transformers. I've never thought about, design an equivalent circuit model purely based on LC elements. You can probably do that, but it's gonna be frequency limited, probably. You can only implement at a certain frequency, I think, because those transformation ratios here are pretty, it's a current ratio of the characteristic modes, so it's pretty, remains pretty constant over a relatively wide bandwidth. In other words, it's kind of frequency independent relatively.
But if you are using a ladder network, it is frequency independent kind of, or a wideband network.
What network you said?
Ladder network or a
ladder network. Oh, I see. But you still.
Why I'm saying is that because in many of the decoupling networks which are available in the literature, they are using LC network basically, which decouple those things. They are very popular.
Yeah. I'm aware of some of them work as well. Yes.
Because transformer network is very rare in the MIMO antenna. That's why I was curious that is it the only solution, or there are possible solutions with the help of this transfer function. What you are solving is.
I see. Very good question. I don't think I have an answer right now. Yeah, but I like your question. I don't have an answer actually.
Thank you very much.
Yeah, thank you for your question.
Okay, I think we have been much longer than expected. Thank you so much for this very good presentation, Binbin.
Thank
very
you.
Insightful to have the circuit theory that we are so much used to, and the characteristic mode theory as well.
Okay, thank you.